morning. Sorry about that. But as I said, this is mainly to try to give you an idea. So we were left over with this cosmological moduli problem. So where I was telling you that it's hard to stabilize the moduli, but one should not just give them a mass, but it has to give them a large mass. So let's see what it means. So let's say that you have found a minimum. Then you can expand the theory around the minimum, and the theory will look like something like this: 1/2 m squared phi squared. The potential can be very complicated, but around the minimum it will look like that. So let's say something like this, where I shift the field. Yeah, I can feel the yeah. So this has got a minimum at 0. So you can always shift it to get it at 0. And this would be some kind of 0 temperature potential. But then during inflation, what happens is that there are extra sources of energy because of inflation, and fields like the volume or the dilaton, as we've seen before, they couple to any source of energy in the theory. So basically what happens is that there will be an extra contribution to the scalar potential that is equivalent to a kind of effective mass for phi that will depend on the Hubble constant during inflation, h, let's say h inf squared. And in general, these will give you a minimum at a different point, some kind of phi minus phi 0. Now, inflation is supposed to take place at very high energy scales. So basically, these can be approximated during inflation as h inflation squared phi minus phi naught squared, with m, that is the mass of the moduli, that is supposed to be much smaller than h inflation, right? So if something like this happens, then basically during inflation, this potential becomes something like this, let's say, where this is my phi 0. So the field is shifted away from the minimum. This is what happens because of the inflationary energy density. And then you should see what happens after the end of inflation, where inflation ends. All the energy there is some kind of reheating, gets transferred into the production of the standard model particles. You have a thermal bath that redshifts as radiation, and H starts decreasing up to a point where this potential somehow approaches the other potential, okay, the 0 temperature potential when H goes to 0. But then one has to look at what the field does, and to look at that, you need to look at the Klein-Gordon equation in an expanding universe, which is phi double dot plus 3h phi dot minus m squared phi equal to 0, when you consider just the dependence on time. And you see, this is a standard harmonic oscillator plus a friction. So at the beginning, when h is much bigger than the mass, this potential starts approaching the 0 temperature 1, but the field is stuck here, right? Because this guy dominates, which is the friction. This field will instead start oscillating around the minimum when this term starts becoming important. So when h decreases, so the universe expands, cools down, h decreases. At a certain point, h becomes of the order of the mass, and the field will start oscillating with an initial amplitude of order phi 0. So when h oscillation is of order the mass, phi starts oscillating that's fine, and it stores energy. So it stores energy So it will start oscillating classically around the minimum, and this behaves as a condensate. So it will redshift as matter. So one can check at this point what is the energy density into this field and compare it with the thermal bath, right? Because you have inflation, then you form a thermal bath with radiation. Then there is this field that the center point starts oscillating and also gets some energy density. So one has the energy density of phi when it starts oscillating. This will be of order of this potential. So it will be of order m squared, now phi naught squared. And what you expect in general for these fields, which are gravitationally coupled, is that this phi naught is of order the Planck scale, which is what you find for the volume mode, for example. So this will be m squared and Planck squared. Now you need to compare it with the energy density that is in radiation. So with gamma, I mean radiation in the thermal bath, os, which means when this guy starts oscillating. So this from the Friedman equations is m squared, it's h squared and Planck squared, where h is at the time of oscillation, but we know that this is m, so this is m squared and Planck squared. So you see that when this guy starts oscillating, basically almost immediately has the same energy as the background. So these are comparable. However, this is radiation, so that redshifts with the scale factor to the -4, whereas this is matter, so this redshifts as the scale factor to the -3. So which means that this guy very quickly comes to dominate the energy density of the universe. Let's say, but phi quickly comes to dominate the energy density of the universe, since rho phi goes like the scale factor to the -3, and the scale factor increases, and rho gamma instead goes like the scale factor to the -4. Good. So this guy then will start dominating the energy density. All the energy density is in phi up to a point where this field will decay. Now, when phi decays, it dominates the energy density. So it will decay back into radiation, and it will dilute everything that is being produced before its decay, because there is some entropy injection into the thermal bath. And one has to be careful, because if you have this dilution after Big Bang nucleosynthesis has started, you modify the prediction of Big Bang nucleosynthesis. That's the origin of this problem. So let's say the phi decays when h is of order what? Now this will be h decay. This will be order in general. So a field decays when, so there's a quantity that gives you the lifetime of a particle. Is the decay width, right? You take the inverse of that. And this h, when you take the inverse, roughly speaking, it tells you the age of the universe. So when they are the same, when the lifetime is the same as the age of the universe, it can decay. So this should be of order gamma, the decay width for the decay of phi, for example, into radiation. Now this is, well, one can compute it, but it's easy to estimate this, because we have seen that this will be some kind of coupling phi into, for example, gamma gamma, something like that. So this could be a term like phi f mu nu over m Planck. Remember that these guys are gravitationally coupled. Now the width goes like the coupling squared. So there has to be some 1 over m Planck squared here. Then you know that just by dimensional analysis, this case has a mass. So there has to be a mass cube here. These, let's say they are radiations, they're massless. The only mass is the mass of this guy. So you can infer pretty easily that it has to be m cubed divided by m Planck squared. And right, so here h, I thought I said that, but I didn't write it down, is m, h oscillation. Whereas when h decay now is m, so h oscillation times m divided by m Planck squared, then you see that h decay is much smaller than h oscillation, given that m is much smaller than a Planck. So later on, after oscillating, this guy decays. When it decays, it's a situation like that. You can compute, maybe it's a simple exercise. You find that rho phi at decay time, so this is the energy density. This is equal to the energy density of radiation at decay time. You just use the fact that they have a different redshift, times basically a decay over a at oscillation. And this quantity is rho gamma at decay times m Planck divided by m to the 4/3. Now this guy is much bigger than 1. So you see that when phi decays, its energy density is much bigger than the one in radiation. So radiation gets diluted, or everything that has been produced before this decay gets diluted, and you have a new reheating from the decay of this guy. So things get reproduced. However, you need to impose that this reheating temperature, so there is a late time reheating. So there is a late time reheating by phi decay. So you need to impose that this reheating temperature from the decay of phi now is bigger than the temperature at which BBN started. Does any of you know what is the order? Yes, exactly. I mean, what is the order of magnitude of this? So it's for the 1 mega electron volt, 1 MeV. Okay. So then it's a simple exercise. So T reheating can be worked out in the following way. So we have seen that H, when H is for the gamma, we have the decay. Basically, if there is an instantaneous reheating, all this energy that was in phi goes in gamma, and you have a thermal bath again. So you have that H at decay is the one basically the thermal bath that gets formed after the decay, so at T reheating, which is of order gamma. Now using this, one can work out T reheating. So you find that now T reheating is the square root of gamma times m Planck. We write down gamma as m cubed divided by m Planck. This is the mass of phi, right? Cube. And this will become now m phi square root of m phi divided by m Planck, if I didn't make any mistake. Yeah, that's right. Okay, good. But now you just impose that this one is bigger than order 1 MeV. Then you get a bound for M5, and you get that M5 has to be larger than order 10 TD. Just substitute the value for M Planck. So this is where it comes from. And very, very interesting implication. And the implication is that it's very, very hard to get standard thermal dark matter in this scenario. One of the main candidates for dark matter was the neutralino, the lightest supersymmetric particle. And people thought that that was a very, very attractive scenario because of the so-called WIMP miracle. So the fact that when you have this particle with a mass around 1 TeV, and you have a thermal freeze-out of this particle, so it gets produced in the early universe via freeze-out. So basically, it is in the thermal bath, and then at a certain point, so it gets produced with the same rate as the annihilation. But at a certain point, the universe expands, and two dark matter particles cannot find each other anymore because of the expansion of the universe, and then you have a kind of freeze-out for the number density. And in this scenario, however, one has to be careful, because if the reheating temperature from the decay of the moduli is below the freeze-out temperature, it means that if you produce dark matter, it will be diluted. And then the standard WIMP miracle does not work. And actually, let me maybe write it down. So it's hard to get thermal neutralino dark matter with M dark matter, let's say of order 1 TeV. So this gives rise to a freeze out. F is for freeze out. Temperature, which is of order M dark matter divided by 10. One can compute this. It is independent of the initial conditions because of this thermal bath production. So these will be of order 100 GeV, right? So if you have a 1 TeV mass. So this implies that to avoid, let's say, the cosmological moduli problem, now let's say that we have also modulus, we need to have the mass, the moduli, which is above 10, something of order 10 TeV. So let's say that to avoid the cosmological moduli problem, so the mass of phi, let's say, should be greater or equal than something of order 100 TeV, right? So in that case, you're fine. There is no cosmological moduli problem. You know that you decay before BBN. But in supergravity, in general, the mass of dark matter, so in this case would be a WIMP, let's say a SUSY WIMP. It's generated after breaking supersymmetry. So it is of the same order as the gravitino mass. And in general, the same effects that break supersymmetry give a mass to phi. So there is this general relation. And by the way, are you all familiar with the gravitino? No. Okay. So roughly speaking, you know the Higgs mechanism, how it works. So there is a gauge symmetry, and you can think of that first as a global symmetry that gets spontaneously broken, and you have a Goldstone boson. Then when the symmetry is local, you have the gauge boson that becomes massive by eating up the Goldstone boson. Now the situation here is similar because we've seen the supersymmetry becomes supergravity when it is local. So if you start with global supersymmetry and you break it spontaneously, you have a Goldstone particle. Now it's a Goldstone fermion in this case because the generators are fermionic. Now you make it local, so you have the gauge field, which is the gravitino. And what happens is that if you break a local supersymmetry, then the gravitino eats up the Goldstone fermion, and becomes massive. So when you break supersymmetry, M 3/2, the gravitino is a spin 3/2 particle, the supersymmetric partner of the graviton. This becomes massive. So when this is different from 0, it means the supersymmetry is broken, and you generate a mass for the supersymmetric particles, which is of order of the gravitino mass. And these effects in general generate also the potential responsible for giving a mass to phi. But then you see that if you have that, what happens is that the mass of the dark matter particle is not 1 TeV anymore, but then you will have that the mass of the dark matter particle would be 100 TeV, and then you have dark matter overproduction. If you try, you produce too much dark matter thermally, so this doesn't work. So you need to consider a situation where the mass of the dark matter is much smaller than the mass of phi, which is of order the mass of the gravitino. There are models where this is possible. Basically, these are models, these are called sequestered SUSY breaking. So this basically is the situation when the minimal supersymmetric standard model, EMSSM, is realized with open strings on D3 branes. So D3 branes are 4-dimensional objects which are space-time filling. Space-time, I mean Minkowski. 4D space-time filling in order not to break Lorentz invariance in 4D. And so from the point of view of the extra dimensions, they look like a point, and they can give rise to the standard model or its supersymmetric generalization. Supersymmetry is broken by the dynamics of these closed strings in the bulk. So you see, given that this guy is a point localized somewhere in the extra dimensions, you have a kind of decoupling between the sources of supersymmetry breaking in the bulk and the D3 brane at the singularity. And that gives you this kind of sequestering. So you sequester, so you put apart the standard model from supersymmetry breaking. And because of that, you can get this suppression. And then you can say, oh, but this is good, because now I can have that this guy is of order 1 TeV, and this guy is much higher. But we've seen that when this guy is of order 10 TeV, its decay, its reheating temperature is 1 MeV. But now we need to have T reheating, which is larger than T freeze out, right? T freeze out is now pretty large, is 5 orders of magnitude larger than the BBN scale. So which means that M5 should be very, very large. You can check, and this is true if M5 is larger than 10 to the 7 GeV. So this means that there has to be really a very big hierarchy between the gravitino mass phi and the dark matter to make it work. Is that clear? Because what happens is that if M5 is lighter, I will have the T heating is below T freeze out, and you dilute thermal waves. And I tried, and other people tried a lot to work out scenarios where one gets enough sequestering, but it's extremely hard to make it work. So which already leads to a pretty interesting prediction, somehow from string compactifications, that you should not expect dark matter to be what was supposed to be the standard candidate. So there should be some kind of non-standard production mechanism. And for example, given that you expect to be in the opposite situation, where T reheating is below T freeze out, what happens is that all the dark matter that has been produced before gets diluted by this decay, and it gets reproduced from the decay of phi. But now it is not a thermal production, it is a non-thermal production, because this guy is out of thermal equilibrium. This is not in the thermal path, because it is gravitationally coupled. Remember, this 1 over Planck. So this coupling is too weak to make it thermalize. And then there are different predictions for the mass that can lead to different signatures. Okay, let's move on with another problem, typical problem of moduli stabilization, and is the so-called Dine-Seibert problem. So this is just to say that you need to develop a potential with a minimum that gives a very large mass. But then this problem is associated to the fact that it is not enough, as I said earlier, to develop a potential, but you should find a minimum in a region where you trust the effective theory. And basically, this tells you that if you want to trust the effective theory, you might not find any minimum. Or vice versa, if you want to find a minimum, it is not where you trust the effective theory. So there is this kind of tension. And let's say it's hard to find a minimum where the effective theory is under control, because there are some moduli, like the volume of the extra dimensions, that is flat at 3 level. So let me try to elaborate a bit more. So I have V, the potential at 3 level for phi is 0. So to generate a potential for phi, one has to look at corrections, let's say quantum corrections beyond the leading order. And generically, this has got 3 types of contributions. So there are 3, roughly speaking, contributions. So these are corrections beyond 3 level. So these are G string corrections. So V G string. So these are string loop corrections, which are very, very hard to compute. There are complicated worksheet computations. Then there are corrections that are still at 3 level in G string, but they are higher derivative, as I said earlier. These are alpha prime corrections. These are loop corrections in your worksheet theory. And these are two perturbative expansions, but then one can have also non-perturbative corrections. Now, so you have string loops, which scale, roughly speaking, as there is an expansion. So there is a sum that is controlled by some power of the string to the n and some potential. And we've seen that this guy is a modulus. G string is a field. So G string is 1 over the real part of the axodilaton, S. And computing all these corrections is something that is not feasible. So what you do is that somehow a priori you assume that this guy is, so the real part of S is big. As I said earlier, that this one is small, so that you can trust this expansion. Of course, this is something that allows you to generate a potential. You need to find the minimum for this potential, and a posteriori, you need to check that this is true. Otherwise, the whole procedure doesn't make sense. Then you have a higher derivative alpha prime corrections. And again, they scale, roughly speaking, there is some sum over m, alpha prime to the m, and then you have some Vm. And again, we've seen that this is also controlled by a modulus, because we've seen that the volume of the extra dimensions, so the volume of y6t, we wrote it down as V times L string to the sixth, but this is V. We can write L string in terms of 2 pi square root of alpha prime. So this will be 2 pi to the sixth alpha prime cubed. So then you see that alpha prime divided by 2 pi squared volume to the of the y6 to the 1/3 to make it dimensionless. This would be 1 over the volume to the 1/3. So now you understand why trusting this expansion means that this quantity now should be small. So the volume should be large. And again, it's the same procedure as before. You assume that this is true because people cannot compute all these corrections, and you check a posteriori. The third, these are non-perturbative corrections. In G string, for example, there are also worksheet instantons, but let me just consider these ones. So these will be some sum P, whatever. Then these are typical corrections that are non-perturbative. So these are the exponential suppression factors that I mentioned earlier on. There is some instanton action there, and there is some potential, let's say, the whole thing is a potential. This is some kind of coefficient like that. And again, here in general, you have an expansion. Now, let me try to, at least in a very, very simple example that is very simple to understand, what is the idea behind this problem. So let's assume that we consider perturbative correction. So focus on perturbative corrections. This could be either string loops or higher derivative corrections. And let's say that the potential generated by these guys, you see, it's controlled by different powers of one of my fields, which now I denote as phi. So let's say that the first loop correction or perturbative correction is some coefficient A divided by phi. And then given that is an expansion in inverse powers of phi, let's say that there is something like this, there is something like that. You see, I have 1 over phi, 1 over phi squared, 1 over phi cubed, and so on. And then there will be something of order 1 over phi to the fourth. And where phi can be either the dilaton or the volume. And you see that if all these coefficients are of order 1, as you would naively expect, then what happens? I want to go in a regime where I trust the effective theory. So when phi is big now, because I want to ignore terms, but then, so this potential, if A, B, and C are all 1, and I'm in the region where phi is very big, yes. Yes, so would there be a minimum or not? So if I am in a situation where this is 1, this is 1, this is 1, and this is, I go to a region where this is very big, then this guy has got an extra 1 over phi suppression, this has got an extra 1 over phi squared. So basically there is the leading order term that gives you runaway. So there is no minimum. Well, let's say there are two cases. Let me be more precise. So there are two cases. One is when I trust the effective theory. Let's say I trust the effective theory only for phi much bigger than 1. And as I say, A is of order B, is of order C, is of order 1. Then basically my potential for phi is just A over phi. So this is just a runaway. So this is V of phi, this is a runaway. This is what I said earlier on. You want to trust the effective theory, there is no minimum. The second possibility is instead when I want to find the minimum. So I should be in a situation where the second and the third term are important, right? I want to balance this runaway against these other effects. That's why I put the minus sign here, assuming that all of them are positive. So the second possibility is to use all terms to find the minimum. And by the way, I included 3 terms because that is what you need. Is the minimal amount of terms you can check to get a minimum with a positive vacuum energy. Then it's an easy computation. You can compute V prime of phi and you set it equal to 0. There are, you get a quadratic equation. There are 2 solutions, phi plus or minus, which is B over A, the usual, 1 plus or minus square root of 1 minus 3A divided by C over B squared. Where here you see that you need to impose B squared greater or equal than 3AC. Basically, when this is not satisfied, we are basically back to the solution we've seen before. Whereas when I have the equal sign here, these 2 extrema coincide. And then when I go to B squared larger than 3AC, I have 2 extrema One is a minimum and the other is a maximum. So you can compute also v prime prime. So let me set, because I want to get the minimum, b squared that is greater than 3ac. So you have that v prime prime, it's easy to compute. In v minus is positive. So this is a minimum. And v prime prime at v plus is negative. So that's the maximum. And let's say that you want to have that the minimum, so v evaluated at v minus, so at the position where the minimum sits. Let's say we know that the cosmological constant is basically 0. So let's say that I want to set it equal to 0 so that I have a potential that looks like that, right? With phi plus and here phi minus. This tells me that it's a simple exercise, that AC is equal to b squared over 4. And now you can substitute back here and you find that the minimum, phi at the minimum, becomes equal to b over 2a. Okay. Now remember that we want to be, is that right? Yes. We want to be in a regime where we trust the effective field theory. And this is always the case if phi is big. So we want to have these much bigger than 1. Then you can say, well, that's fine. I need to have just b much bigger than a. So let's say that a is of order 1, b can be of order 10. Something like this. Okay, that's fine. But if I do that, basically what happens is that it is true that phi is big, but when I evaluate these now at the minimum, is the one that gives me 0. So you evaluate these at phi minus. Basically, this term goes like 2a squared over b. Clearly, this term is of the same order, because otherwise we would not get the minimum. And this term here is also 2a squared over b. And that's why you get the cancellation. But now do you see something wrong here? No, we don't want the potential to be flat, right? We want to get the minimum. But the problem is that now all of these terms are of the same order. So we don't trust perturbation theory. So who tells us that we can ignore this term? And in fact, how is this possible? Because phi is big? Well, because we have tuned basically b. So in the end, we will have c much bigger than b, much bigger than a. This is what happens in this case, right? And so these are kind of tuning. And again, it is not clear if you can trust effective theory. Okay? Now, what would be a way out to this problem? Because, this tuning is not even known if it is feasible or not. You might not, because in theory, one could say, well, maybe I have these other terms that go like 1 over, there will be some d divided by phi to the 4th. Maybe d is 1, and then I can really ignore it. But who tells me that I can do this tuning, and once I tune this coefficient, this does not also become big, and so on. So what could be a way out? So you see here, the problem was that I was trying to find the minimum by balancing different terms in the same expansion, right? Because to find the minimum, you need to balance different terms. So the suggestion could be Because remember that, okay, I erased that. Oh, no, I didn't erase it. You see, there are different corrections. There are different expansions. So if I, for example, term in this expansion with the first term in that expansion, in theory, things can work. There's nothing wrong with that. It could be that the second, third terms are much smaller than the first. Here, the second and third term are much smaller than the first, but the first scales as the first here. Or the same is true with non-perturbative corrections. So try to find the minimum. So let's say do not balance different terms in same expansion. But different terms in different expansion. So like you can have alpha prime corrections which are balanced against G-string corrections. This is something that we did recently in a paper with Ahmed to have a good embedding of brain anti-brain inflation. So this is called perturbative stabilization. Perturbative stabilization without using non-perturbative effects, but based just on perturbative corrections. Or another possibility, so let's say this is one, that is two, balance perturbative corrections against non-perturbative ones. Which sounds a bit odd, right? Because you expect non-perturbative corrections to be tiny. They are non-perturbative. But it could be that given that the guys that appear here, they're moduli, so they're fields, and also here there will be fields, it could be that these are different fields. I will show you an example in such a way that these two guys can compete naturally without any fine-tuning. Okay, good. So these are all the problems that are there for moduli stabilization. And I said this morning that the first attempt to do moduli stabilization or to do string phenomenology was the theoretic string. But the theoretic string, we already seen this problem with AlphaGut, that it's hard to trust the effective theorem. And on top of that, as already mentioned by Ashok very quickly, a source of the potential for most of the moduli are fluxes, are background fluxes that you can turn on in the extra dimensions. And in principle, one could do that in the theoretic string, in the type 2b string, type 2a, and so on. The problem is that these are sources of energy, so they gravitate, so they back react on the geometry, and in the case of the theoretic string, they tend to destroy the background. So the background is no more a Calabi-Yau, something more complicated, and again, it's hard then to derive the effective theory. Whereas in type 2b, the good thing is that you can turn on these fluxes that help to fix many moduli, not all of them, but their back reaction on the Calabi-Yau, their gravitational back reaction is mild and makes the Calabi-Yau only Calabi-Yau up to a warp factor in the metric. So one can still have control over the effective theory. And on top of that, another problem with the theoretic string is that in the theoretic string, everything lives in the bulk. We've seen that the non-abelian gauge fields are closed strings, right? They are actually, well, maybe you've seen it, how they come along. because the theory has got fermions only in one sector, in the right moving sector, and then you need to compactify. You get this rank 16 gauge group. But you have that the moduli and the standard model gauge fields, they're all closed strings and they all live in the bulk. So somehow reproducing the standard model and doing this and stabilizing the moduli is, there are two problems that they are coupled because they deal with bulk physics. However, in type 2b, that's why all cosmological and phenomenological applications so far have been focused on that. There are branes, and branes are very good because they allow you to get the non-abelian gauge bosons. So branes were discovered in the mid-90s, and then people realized that thanks to branes, one can get the standard model out of type 2 theories, type 2a and type 2b. And then the nice thing is that you have that now the standard model is reproduced with open strings, which live on branes. And so that's the problem that is localized somewhere in the X dimensions where the branes sit. The problem of reproducing the standard model with the right gauge group, Yukawa couplings, chiral spectrum, and so on. Whereas the moduli are closed strings, which live in the bulk. So the two problems decouple somehow. So there are several advantages. So let me list them. So type 2b, string pheno, received a lot of attention after the discovery of branes, of the branes, and let's say for several reasons. So the presence of the branes provides so non-abelian gauge symmetries and chiral matter. Non-abelian gauge symmetries and chiral matter as in the standard model. So one can have, for example, intersecting stacks of branes. So some of you told me that you've seen these things in one of the preschool lectures. And so, for example, you can have M of them, and here you have an SUM gauge group. So here you have an SUN gauge group. So you see this could look like SU2 times SU3 in the standard model. And so there are here open strings, which would be the adjoint vectors of SUM and SUN. And then you have also strings at the intersections, and these are these are matter fields. So this will be matter in the bifundamental representation. So it would be MN, the representation. So that's how you get, let's say these are the adjoint vectors. On top of that, one can, as I said earlier, turn on these background fluxes with a mild back reaction. So one can still have the background, especially the moduli space, under control in a certain sense. So one can turn on non-zero vacuum expectation values for background fluxes. So we're seeing that in the massless spectrum of the string, in the Ramond-Ramond sector, we have C0, C2, and C4. There is also the B2. Now, each of them has got the corresponding field strength in terms of forms. And now these guys can have non-zero fluxes in a way similar to what you have seen in electromagnetism, right? In electromagnetism, when you have you want to measure a charge, you consider a sphere surrounding this charge, and then you look at the flux of the electric field through this sphere. Or in the case of a monopole, you look at the flux of the magnetic field. And here is similar. So, for example, if you take F3, now you will have to integrate over what? Over an object which has got dimensionality equal to, right? In the case of a standard electromagnetism, you will have, in the case of electromagnetism, you have this, right? Which is F2 equal to the A1, 1,4, right? So in that case, this would be F2 in the case of the monopole. So in the case of the, would be star F2 in the case of the Gauss law. And you integrate over a sphere, right? So here is something as a tree form. You need to integrate over something that's got dimension 3, right? So this will be a 3 cycle. So an object without boundaries, and it is 3-dimensional. And these guys are integers now. This is basically similar, it's the same story as the quantization condition that maybe you've seen, the Dirac quantization condition in electromagnetism once you have monopoles. And there is a 9 here because in a Calabi-Yau, so this will be some kind of 3-dimensional submanifolds of your 6-dimensional Calabi-Yau. And of course, in a 6-dimensional space, you can have several 3-dimensional submanifolds, which are labeled by I. And then you can have something similar for H3. Let me call it the Mi, a different integer. And these are labeled. So I, again, this is a number of 3 cycles of a Calabi-Yau. This is given in terms of these Hodge numbers. So these are 3 cycles. And now these are sources for the potential of many moduli. You see this intuitively. For example, there are some, especially the complex structure moduli that I mentioned earlier, they are volumes of 3 cycles. And then you see that effectively you generate some energy that depends on the volumes of these 3 cycles. And then it can be used to develop a potential for these fields. Now, this guy, one should have an integral over a 1 cycle. And this will be 5 cycles, but these are not there for Calabi-Yaus. So there are no non-contractible 1 cycles. So these are the fluxes that are there. And these fluxes, they generate a potential for the axiodilaton. and the complex structure moduli. The complex structure moduli. And this is a 3-level, semi-classical, let's say, because of this quantization condition, but it is a 3-level. With a small back reaction on Calabi-Yau geometry. So this means that basically the metric looks like this, ds squared, where it is e to the 2ay. Let's consider the case of Minkowski for dimensional. Then you have the Calabi-Yau metric, GMN of y, dym, dyn. So this will be my Calabi-Yau metric, and this is the warp factor. So turning on these fluxes amounts to generate a non-trivial warp factor, but still this metric is Calabi-Yau. So you can have, so this means that you can fix most of the moduli. I say most because this does not generate a potential for the Kähler moduli. Okay, so there are still, for example, the volume is not fixed. So fix most of the moduli with an effective theory that is under control. On top of that, 3, there is a so-called brain world scenario, which is what I said earlier. So these are all the good features of these compactifications, because gauge interactions, so gauge interactions, we've seen that are open strings. So these are open strings. So these are localized. On brains. While the moduli, which we are seeing are closed strings, propagate in the bulk. So somehow this means that physics decouples, at least at the leading order. It is not true completely, of course. So this means that one can study separately the problem of reproducing the standard model and moduli stabilization, because one is a bulk problem, the other is a brain problem. And then once you have found the two solutions, you can try to combine them together in a fully consistent effective theory. So can study two problems separately, and this is actually how separately historically the field developed. So these two problems are getting the standard model and moduli stabilization. Okay. Yes.
Sorry, so the speech in the previous time was you were talking about the moduli stabilization in cosmological theory, right? Like, so are we still doing that? Because like to choose like like external dimension with that, like here. So I was still talking about the moduli stabilization in like physical. Like this.
No, you can have. I mean, everything that I said here applies also to inflation, for example. So if you want to, have let's say a system that evolves, that's fine. But somehow this is in the end what you should get for the global minimum of your potential, right? You should get something that, I mean, it's a de Sitter, but very, very close to Minkowski. And then you can see cosmologically how you get there. Okay. So for example, before I was drawing this kind of potential, right? Now let's say that this potential maybe it's like that in this direction. In another direction, could look like there is a global minimum, but could look like that. And now when I'm here and then here, I would be basically Minkowski, but I can think of this cosmologically as a system that evolves towards that.
And how do we know that the equation of motion elementary was not satisfied?
That's a good question. So let's say that once you look at the effective field theory and you try to minimize the potential, basically that is equivalent to solving the 10-dimensional equation of motion. And if you trust your effective field theory, then this should work. This is the whole point of effective field theory, right? But at a certain point, if you trust things, you should also be able to see that from the 10-dimensional point of view. But as long as the effective field theory is under control, you find that these minima are a very large volume and weak string coupling. The scales decouple, and I mean, effective field theory works. So, at what time should I stop? 15. Okay. So, let me draw a picture. Pictures are nice, and maybe let me leave it here. So the pictorial view is the following. Let me see if I manage to draw something that is understandable. So let's say that this is my Calabi-Yau, right? So this is a very non-trivial manifold. There could be holes. Let's say it's topologically non-trivial, and for every point in the extra dimensions, you have Calabi-Yaus. And there are closed strings which propagate in the bulk, and these are the closed string moduli which propagate in the bulk. So this could be the volume mode, the dilaton, and so on. And then you have branes. So the kind of branes that you can have depend on the particular type 2 theory that you have, type 2A and type 2B. But then it depends also on the kind of orientifold involution that you choose to go down from n equals 2 to n equals 1. And for example, let's consider a situation where, given that I mentioned type 2B, a consistent possibility is with D3 and D7 branes. And so, for example, you see that a D3 brane, you see this couple to these fields here, right? So there's a coupling between branes and Ramond fields. What did I want to say? Yes, that now when you have a D3 brane, so this is a 4-dimensional object. So this guy, in order not to break Lorentz invariance, has to be space-time filling. So from the point of view of the Calabi-Yau, then it sits at the point. So let's say I have something here And here I can have some space-time filling D3. I can have several of them, D3s. And another point of the Calabi-Yau, I can have more D3 branes. Why not? Of course, let's say they are charged objects, and there are some consistency conditions, because one has that in a compact space, the total charge has to be 0. This is the tadpole cancellation condition. So you cannot add as many as you like. There are fluxes which contribute, and branes or planes and so on. So there are the 3 branes here. And this guy instead, the 7 branes, they are 8-dimensional objects. So they are space-time filling. So 4 dimensions are filling Minkowski. So which means that in the extra dimensions, they should wrap some cycle with dimension equal to, let's see if you're with me, 8. Who offers more? So these are 8-dimensional objects, right? Now, 4 directions are in Minkowski. Then you're left over with 4. And these 4 have to wrap some 4-dimensional submanifold in the extra dimensions. So this is called the 4 cycle. So let me depict it in this way. So let's say you have some kind of the 7 branes, which wrap with this, I mean Minkowski, but then they wrap some internal 4 cycle. And then also here you can have several of these stacks. You can have another here that is wrapping here an internal 4 cycle. So these are also the 7 branes, and there are open strings on all of them. So it could be that this is the visible sector. So it could be that, for example, here you have the standard model. So at that point, this will be some kind of hidden sector, because the open strings that are here are not charged under the standard model gauge group because of the separation, the geometrical separation in the extra dimensions. But the same is true also for the 3 branes. One could also build the standard model with the 3 branes. So in that case, this would be a hidden sector again. So let me write visible twice just to mean that the standard model can be here or here. And this could be also some hidden D3 branes. And the nice thing is that the gauge coupling of the theory, so here if you have an SU n theory, if you have n of these branes, so the gauge coupling of this Yang-Mills theory to the -2 is given by the volume of the 4 cycle, sigma 4, that is wrapped, which in turn is one of my moduli. So let me call it, well, for example, if I have only one modulus, this will be the volume of the extra dimensions to the 2/3, right? Because this is something that has got dimension 6. So it's like a length to the 6th. So this becomes a length to the 4. So you see that the nice thing is that the vacuum expectation value of these closed strings determines the value of the gauge coupling on the 7 branes. And in the case of hidden D3 branes, so here G Yang-Mills to the -2, there is no volume here. So the coupling that this has to fill is just the string coupling. So it's 1 over G string. So in this case, it is the dilaton that determines that. So if I have 5 minutes, I can maybe show this result. This could be useful for you very quickly. So from the dBi action. You can find that result so that at least you have an idea where it comes from. So let's compute the gauge coupling. So compute the gauge coupling. So you compute the gauge coupling of an SUN theory on a stack of n. Let me write d p brains. So I'm not specifying if these are the 7 brains or the 3 brains. So you've seen, I hope, the Dirac-Born introduction, the dBi action. Did you? You did? Yes? Okay. At least I get an answer. If you didn't, I will write it down. So this is the tension of the brain. It's like the mass for a particle. Then you need to integrate over the word volume of the brain. So this is the word volume of the brain. So a string has got the word sheet, the brain has got the word volume. And if the brain is a p brain, the word volume would be like a word sheet is 2-dimensional, the string is 1-dimensional, this p plus 1-dimensional. Then there are, you integrate over some coordinate zeta. There is e to the minus phi. Then there is a square root minus the determinant GAB. Then there is also the B field, but let me set it to 0. 2 pi alpha prime F AB and the square root. Where this is just the pullback of the metric on the worksheet. So it's how the metric restricts on the worksheet. Whereas this is just the field strength associated to the gauge bosons which live on the brain. Okay, that's good. So now so I have this worksheet, which is, I said that they wrap Minkowski, so they're space-time filling, so is R13 times some cycle in the internal space, which is a p minus 3 cycle. So in the case of the D7 brain was a 4 cycle, 7 minus 3. In the case of the 3 brain, there's nothing. So now what I want to do, I want to compactify this theory on this p minus 3-dimensional cycle and see what I get in 4 dimensions. I should get something that looks like the Young-Mills action, and then I can read off from the coefficient of this action the coupling. So to do that, let me first notice that, so I have the determinant of G schematically plus 2 pi alpha prime F there. Now, this is equal to the determinant of A of a matrix is equal to the determinant of the transpose, but the metric is symmetric. So let's say I have 2 pi alpha prime F transpose. Now the metric G transpose is equal to G. This guy is anti-symmetric, right? So there is a minus. Okay, that's good. So now I want to make an expansion. So I write these as the square root of minus the determinant of G, AB, times the determinant of 1 plus 2 pi alpha prime G to the minus 1 times F, right? Now, let me use this result. This is telling me that this quantity is the same thing as the square root of the determinant of 1 minus 2 alpha prime g to the minus 1 f. Right? This is just this result. So this implies that the determinant of 1 plus 2 pi alpha prime g to the minus 1 half under square root, I can write it down as the determinant of 1 plus 2 pi alpha prime g to the minus 1 f times itself. But now I write it down as 1 minus 2 pi alpha prime g to the minus 1 f. And now this thing is to the 1/4. Why is this useful? Why is this manipulation useful? Well, because now there is an identity that we can use. So you have that the log of the determinant of an operator A is equal to the trace of the log of A. I see people that agree with me. That's good. So the determinant of A is then e to the trace of the log of A. And then let's apply to this guy, because this can also be rewritten as the determinant of 1 minus 2 pi alpha prime squared now, g to the minus 1 f squared to the 1/4. Now let's use this result. So this implies that the determinant of 1 minus 2 pi alpha prime squared g to the minus 1 f squared. Let's use this formula. Now this is e to the trace of the log of A. Now A is this. So it is 1 minus 2 pi alpha prime squared g to the minus 1 f squared. Now you know how to do the expansion of the log of 1 minus something. So you will get e to the minus the trace of 2 pi alpha prime squared g to the minus 1 f squared plus higher order terms. And now you can keep expanding, because you know also how to do the expansion of the exponential. So this will be 1 minus 2 pi alpha prime squared. Sorry, I want to get this. So let me be, this thing is to the 1/4. So let me do it already here to the 1/4. So if we do this to the 1/4, I get a 1/4 here. I get a 1/4 here. So I get this divided by 4. And I get the trace of g to the minus 1 f squared plus higher order terms. Now you see that I should put this thing here, and you see that this action starts looking like the Yang-Mills action, because this guy, this trace is equal to g AC f CD g d b f b a, which is basically f ab f ba which is also equal to minus FAB, sorry, FAB, FAB, which is what you are familiar with. So we're almost done. So now you plug it back in the dBi action. So you find that S dBi is minus Tp. Then you have the integral over the word volume, P plus 1, d P plus 1 zeta e to the minus phi, square root of minus the determinant of G. And then you have 1 minus 2 pi alpha prime squared divided by 4 FAB FAB plus dot dot dot. So now you compactify here. So you do a dimensional reduction, integrating over this P plus 3-dimensional cycle. So you find that the dBi action will include a term that goes like minus Tp, the volume of sigma P minus 3, right? And then you will get e to the minus phi 1 over 4 2 pi alpha prime squared, and then you have the integral over the 4x, and then this is a situation where these indices now are space-time ordinary indices, and you have f mu f mu. And now basically you can read off the coupling, because you can write it down as the usual Yang-Mills action in 4D, where actually there is a trace here, but doesn't matter. Like this. And then you can read off G, Y, and Mills squared in terms of the volume of symmetry. You see how it comes out, and the dilaton. So you find that G Yang-Mills to the minus 2 is equal to the tension of the P brane, 2 pi alpha prime squared, the volume of sigma P minus 3 times e to the minus phi. And if you write these as, I'm done. So this is the last equation. So 2 pi is m string to the P plus 1. This we write it down as 1 over 2 pi squared m string to the 4th. This we also write it down as a dimensionless quantity, as we did before. Now let me call it tau P minus 3 cycle times m string to the P minus 3. So we write down all these powers of m string. You find that this is tau P minus 3. So the powers of m string cancel off, divided by 2 pi e to the minus phi. That's the result. So in the case of a D7 brane, now you understand what I said earlier. 7, P is equal to 7, so you have the volume of a 4 cycle divided by the dilaton, so which is basically the volume of the 4 cycle in Einstein frame, because that's the one in string frame. Whereas for D3 brane, P is equal to 3, and you just have 1 over G string. Okay, let's stop here.